So, hello, I am Renaud Savalle and I work at Paris Observatory in the PADC group, which is the Paris Astronomical Data Center. I'm also a member of the Wivona project, just described by Jean-Paul. As you know, it's a pro-am project funded by Paris Observatory, which objective is to help disseminate the VO data and also the VO techniques and standards accessible to amateur astronomers. So I will begin by defining the astronomical virtual observatory. As Jean-Paul mentioned, it's not a website. It's not a set of websites because these disappear. It's not a program either because they become obsolete. But it's a long-term effort. We're talking about dozens of years. The VO itself is only 20 years. And as said before, it groups about 50 data centers in the world in about 20 countries, which host astronomical archives. It groups a lot of people, data publishers, curators, operators, and they run services and they run the central infrastructure, the registry, which is a distributed database to discover the data collection and the services. The VO also is constituted of editors and writers of standard protocol that we write to allow discovering and accessing the data. And of course, developer of client application. So this is a good definition by Wikipedia here that I've put for reference. So the challenge of the data in the virtual observatory is that it is very big and it is very various. So we have images that are reduced to catalogs, which contain individual objects with a lot of characteristic or columns. And as the volume decrease of this data, the knowledge actually increase. We also have spectra and time series and more advanced data types like spectral cubes. So I work for the International Virtual Observatory Alliance. So I'm going to describe a little bit what it is. It was founded about 20 years ago and with 23 member projects and countries. You can see here the national VOs like EuroVO, the European VO. And it holds 2 interoperability meetings per year where we have discussions about a week long and presentations to make our tools compatible with each other. The vision of the IVOA is threefold. So first, develop a fair data management framework for astronomy using our standards and publishing tools for data centers. Also, we want to enable new science through the virtual observatory. This is going to be multi-wavelength science, typically, to combine datasets from multiple sources. But also, we need to be making discovery tools and to make new research. We also work on data analysis and visualization tools like Aladdin. So thirdly, the IVOA is a worldwide collaboration. There is no formal funding. Instead, it's funded by national projects and observatories. And it's very diverse. We have people from all around the world. So a few high-level standards that you may already know. There are several kinds. So there are standards for designing applications, such as VO table, which allows to exchange tabular data with accompanying very rich metadata. We have HIPS, Hierarchical Progressive Survey, which is tailored for displaying large data volumes. And we have also standards to discover and transport data. You are probably familiar with VO event. We have also simple console, simple image access, and simple spectral access to discover data of catalog, image, or spectral type in a certain area of the sky. We have MOC, TAP and ADQL, which allows to make those complex queries I was telling you about. Also, OBSCORE for describing observation. We have the registry standards and we have also standards for planning observations. So the architecture, uh, you can see that the VO is a necessary middle layer between the users and the providers at the bottom. And like the web, which enables end users and machines to access documents and services wherever and however they are stored, the VO enables the astronomical scientific community to access resources wherever they are and to access them the same way. So the core component is made of query languages and data models, semantics, which include vocabularies, and formats. And then around that, you have the registry, which helps finding the data, and the data access protocol, like simple search, which allows to query them. So if you put all the standard and more that I showed before on this diagram, you see that they are the core components, and this standard spread across a large range of different domains. So this architecture is fair. In fact, the virtual observatory has been fair from the beginning. So if you look at this diagram I showed there, you see on the left, you see finding, using, and you see sharing, you see getting. And this was designed before publication of the FAIR principle by Wilkinson and Dumontier in 2016. We have the findable, the interoperable, the accessible principles, and all this is reusable. There is an interesting article published about that by the current chair of the executive committee of the IVOA. The reference is on this slide. So about this organization, the IVOA is made of several groups. First, the executive committee here. The science priority committee links with the data scientists with other scientists. For example, there was a request some years ago to investigate the high energy domain, and this led to the creation of an interest group. The technical coordination group is made from several working groups, 6 working groups, which specialize in one aspect of the architecture I just showed, and they define standards related to this aspect. And the interest groups here are more thematic. They push and evaluate standards within their domain of interest. There is also a IVOA IAU liaison group here, which I mentioned because it's important to consider that the IVOA has been engaging with the IAU to support the astronomical goals of the IAU. For example, IVOA standards can be endorsed by the IAU. IAU as a working group, virtual astronomy and data centers in Commission B2. And on the other hand, the IVOA promotes the usage of the unified astronomy thesaurus, which is endorsed by the IAU. So I'm going to show a small demo with a use case using this unified astronomy thesaurus. The goal will be to locate the VO resources containing data collections related to gamma ray burst using a UAT term, a term standardized by the IAU in the unified astronomy thesaurus. Then we'll use a simple search service for these resources to search for objects in the sky in an area of the sky. Then we will save the objects found in a file. So I'm going to use the Python language and demo it with Prism because it has a Python console as mentioned by Jean-Paul earlier. I'm going to use the PyVO package version 1.7 to be specific. So bear with me while I change my screen. First, I'm going to show you the program. So here we import the necessary packages. We check the version here, and we do some housekeeping to remove some possible warnings. And we're going to use the registry module of PyVO, and we're going to use it to search for this term, which is a standard in a standard vocabulary of the UAT. We're going to use this function registry.search to and provide it with a parameter which is a UAT constraint using this term. Okay, and then we're going to print the number of resources found. Then for each of the resource, we just show what its short name is and what its title is. This way, we will know in the registry all the resources which have been registered using a subject containing the term gamma ray burst. So this is useful if you look for a certain area of the sky, for example, and you want to know the GRB that has happened there. Then we're going to do a cone search with these coordinates where I know there is something. And I'm going for the simplicity to query only the first resource found. We're going to first get the service of type cone search of this resource. So the resource contains data and it also has a service. So here we ask for the service, okay? And then we're going to launch the cone search here and convert the results to a table and print this table, okay? And then the rest is saving this to a comma separated value file and to a VO table file. We'll do that and I'll show you the table after. So now I'm switching to Prism, and here in Tools I can find the Python console. So I'm going to load my script here, which displays here. So this is the same thing I display. I just use an editor to show you the syntax better. We don't yet have the syntax coloring. And then I'm going to execute my script here. You see it goes very fast. So let's go through the output. So we see that 92 resources were found in the registry about gamma ray burst. And this is a list of all the resources. You see there are some coming from Vizier, some coming from astrophysical journals, and so on. I'm not a specialist about that. Some coming from NRS and different catalogs. So after that, I told you I was going to query the first catalog. So this is at this concert URL, and I retrieve 5 rows. So this is probably 5 GRBs. And the associated data for each of them. We have a position column and other columns. And then I save that to a CSV file and a VO table file. So let's look quickly at the VO table file here, which is an XML file containing different elements. So the first element is VO table, the root element, and then you have resources, and for each resource you can have several tables. So here it's a simple table. There is only one resource and one table, and for each, yeah, almost done. For each of the columns of the table, you have a field, and the metadata is rich. You have the type, the name, the precision, the UCD, which is a unified contour descriptor, a semantic description for each column here, and then at the end you have the data. So that is about what I wanted to show you. It's very easy to make scripts like that and to integrate them with Python into software like Prism, thanks to the work of the coders, the developers of Winova. So I will stop here. Thank you for your attention.